All right, well, thank you very much for the opportunity to talk about quantum dots, especially following Quandella's work. That's very nice to have that as the last talk to build up on. And I'm basically, we're doing a number of different things in our labs in Cambridge, but strictly speaking, I'll focus on the quantum dot side, but there's at least one poster here that highlights some other works as well, so I won't tell you what. Go around and find out. All right, so it is quantum technologies technically, thematically, but so I want to start from something much like quantum physics has evolved, starting from foundations and concepts towards technology, from philosophical foundations towards applicability. So in the same sense, I want to take one topic that today we consider to be very technological and exciting, and that's quantum networks. And I want to take a step back just to remind you that actually even that still it has roots quite deeply in the foundations of physics and our understanding of nature. So when you build a quantum network, you might want to take one step back and say, what does it mean? And just take that one moment, a cookie of enjoyment on the foundation principles of it. And the idea is this. The key thing is that we want to create correlations, right? We want two things to interact with each other. And in nature and in physics, this requires proximity. No matter what physical phenomena you're studying, you have to take two things, or many things, that becomes manybody. You take two things and then you bring them close. There's some characteristic length scale over which they can directly interact with each other. And that's the definition of proximity, defining a particular length scale, or at least a length scale dependence for the whole process to occur. Now, that's one of the fundamental features that comes with quantum physics, that you don't need, when you include the concept of light, and hence the concept of light-matter interacting systems, some interfaces that takes matter qubits or matter and links it to light particles. This proximity condition and requirement, foundational requirement, is almost lifted. All I need to do is either have some common mode, optical mode, that energy can be exchanged through these, so that these two species can talk to each other. And if that creates an effective interaction between these two objects, I'm done. The concept and the key requirement of proximity is lifted. Isn't that wonderful? Take a moment. Sure. All right. So the applicability of this, of course, is that you don't have to have a monolithical system approach to whatever it is you're building, you're putting together from application perspective, be it quantum computing or whatnot, unless your intention is to actually go the long distance. You don't have to, but then again, putting everything in close proximity to each other and still having individual access to each one is a challenge. Hence the concept of exploded or distributed structure. So therefore, this optical link it comes in as quite a profound capability to create correlations. The next thing is, do we actually need direct line of sight? You can extend the philosophical discussion and say, does it actually have to be a direct line of sight and direct exchange of energy between the two species or two objects? Can I not have a Puppetmaster, this is this eye over here, that actually interacts with the species directly, separately, and the species don't actually ever see each other. The two objects don't ever actually exchange anything directly with each other, but through the third parties and what the third party chooses to do. In some cases, in this particular case I'll focus on, it's actually polymerization. You can generate, probabilistically, but nevertheless, that's a detail, you can generate correlations between two objects that have never even exchanged light between them. Take that moment again. How profound. Isn't that great that I can get quantum mechanics allows me to take two objects with absolutely no interaction between them and no line of sight and get them to interact with each other and show some sort of correlations, regardless of their location. So imagine this third party is the Puppetmaster with all the possible, say, qubits, for example, and you can pairwise pick any two qubits to create some sort of a correlation. And all you have to do is see them all, have your strings attached to each one. So that concept actually is probabilistic entanglement generation concept. You're not foreign, most of you are not foreign to. And the idea is that if these two blobs, matter qubits, for example, emit light in such a way that I just can't tell the difference between a photon being emitted by one of them versus the photon emitted by the other one, as long as there is entanglement between the matter qubit and the photon that it has generated, which is typical in spin-photon interfaces, it's the definition of it, then this detection scheme is not trying to find out anything about the photon, it's trying to find nothing about the photon. If you're successful at that, then you do create these correlations regarding the internal degrees of freedom. And this was nicely proposed in 1998, and there's been multiple iterations, different approaches to the general concept, including from UK as well. So where does this go to? The concept is indeed what this quite famous plot over here. As long as you have these boxes over here called quantum nodes, and then these red arrows called quantum channels, you're done. That is your quantum computer. All you have to do is find out what they mean in a physical situation, and have all these line of sights to go through your processes, or have this third, which would require that you have these two, say, qubits coupled directly by a single well-defined optical mode, or you have this Puppetmaster approach, so that you have this box, and then the Puppetmaster above is actually talking to every single one of them, and they are not required to talk to each other. That's also nice. And both attempts have been tried in the simplest building block, as in two matter qubits coupled to single photons. Either single photons directly exchange, and that's, I would say, I think the first one is Rampe's results with neutral atoms inside big optical cavities. And the second approach, the measurement-based entanglement generation approach, was first done with trapped ions in the US, but also solid-state BND centers, I think, were the first solid-state systems where a non-atomic, conventional atomic system was used to demonstrate this. All right, so when we say quantum light sources, or systems that offer the spin-photon interface in the solid state, we do like to go to the solid state, or stay there. We do think that solid-state systems offer a number of advantages, and somehow, one way or another, in the abstract sense, speed shows up, bandwidth and speed. Solid-state sources are brighter and faster, and you can drive quicker than atomic counterparts, we keep saying. Now, of these systems, I just listed a few that we work on. There are many more that offer this spin and photon interface. Of these, I would say the quantum dot, indium arsenide quantum dots are the ones we understand most thoroughly. They're the diamond counterparts. Silicon Vacancy Center is the newcomer in the last few years to overcome the complications that nitrogen vacancy centers, despite their many advantages, are facing. So there's going to be progress along these lines. And then there are newer materials where we know less about, and we're studying those right now, but they have offered quite promise. But of this, nitrogen vacancy centers have already been used to demonstrate distance spin entanglement. So why worry? Well, the point was that even though this was used, and these centers were used to really show high quality, high fidelity entanglement, the rates were punishing. You don't want to be a PhD student if you knew that was going to be the rates. By not knowing that it's going to be that slow, they managed to plow through and get the beautiful results. But you don't start knowing it's going to be sub-hertz. You don't start your research saying, I'm going to go out there and achieve millihertz entanglement generation rates for quantum technologies. So we have to find the right, if possible, solid-state system that might actually go beyond the millihertz range. And what I'll talk about today is the self-assembled quantum dots as part of this section. So what I mean by self-assembled quantum dots, these are indium arsenide quantum dots inside a gallium arsenide matrix, small islands, as Nicola explained. But in our case, we don't have cavities. We actually have no cavities in these experiments, but instead we have electrical contacts. That was easier for us to do, and then we thought we'll just integrate along there. Again, we don't know whether it's going to be millihertz or not. That's why it was easy to come and speak. And then the idea is that by electrical contact, we can not only control the amount of charge inside a quantum dot. It could be neutral, so you get bi-exton cascade to generate tiny photons, for example. Or, more relevant for us, we load up a single electron, so then the quantum dot itself in the ground state has spin up and spin down projection, so it's a single electron state, like here. And then the optical transitions will give you a 4-level scheme to do your manipulations and play your games. All right. This is what it looks like. This is a soul immersion lens we glue on top of our sample. That's our nanofabrication. This nanofabrication, if you look through this SIL, soul immersion lens, you get to see the contact, electrical contact on top, Schottky window, semi-transparent, and then if you look inside, on a cloudier day, you get to see the big contrast of the quantum dots. Each of these is a quantum dot, and if you take one of them, you can see that they emit single photons at the top. Great. And this whole thing gives you around, on average, 7 million photons per second at the end of a single mode fiber out of a cryostat. This is at 4K, so you have a small cryostat to run the show. But then, at the end of the day, you can have a single mode fiber, even without cavities, giving you millions of photons per second. I'm saying this, emphasizing this, because it's not that quantum dots were not good and got better. It's that they were always good, and they're getting even better. Right, I'm really selling this. At the moment, quantum dots are the best solid-state sources for photons, and in combination with photons and the matter qubit. That combo, in terms of the brightness and stability and tunability combination, is the self-assembly quantum dots are still not passed. Hence, we like to work with it. Right. So what is it? What happens in the field today is actually these the control and manipulation of electron hole spins with high fidelity, not just proof of principle, but really reaching 99% control benchmarks. The photons themselves, we're now reaching coherence and quality and brightness that is I don't have to repeat Nicola, they're outstanding and best at the moment of any solid-state source. And the communication channel, the improvement of free space versus fibers versus waveguides, take your pick, whatever it is you want to work with. This is, I would say, all of these options are now reasonably mature enough that we can talk about integrating into a larger networks, larger systems. So most of the work is now actually linking them in the most efficient, feasible way. Right. So it's a spin-photon interface, so I need to show you where we are with the spin. We don't do, normally for a spin split system, a spin ground state, it's a magnetic transition. You apply microwaves like you would do, say, for ND centers or in some cases atomic transitions. In our case, we use the strong optical transitions to do the spin manipulation, ground state spin manipulation, using an excited state, but not actually getting there. So with far detuned laser, we're able to do essentially spin Rabi oscillations. This is one example of that, at around 2-3 picosecond times. So in few picoseconds, we do our bit flips. Right? So that's an important feature. And then you can now do these with very high fidelity. We use compound pulse techniques that we go back to old NMR books, and we figure out how to do these things well. And then we're at this stage, we're talking about 98% guaranteed, if not more. And then we do Ramsey just to see the coherence time of the spin. And the number we get is terrible. It's about 1 to 2 nanoseconds. It's terrible, but not that terrible. Terrible because you don't want to say nanoseconds, 1 to 2 nanoseconds, as if it's a win. But remember that the optical transitions are fast. So the reason T2 star is important is because in the process of photon generation, entangled with the spin, I need spin to be, sustain its coherence, so that the entangled spin-photon system, once the photon is generated, sustains good quality entanglement, so high fidelity entanglement. And so this ultimately limits the maximum fidelity that we can expect, but because our photon emission rates are sub-nanosecond, we are actually operating in this window, so we're reasonably okay. So it's worth continuing on with the experiments. And if it's simply a matter of storing the spin, the quantumness of it, not in the process of photon generation, but afterwards, then you do decoupling protocols anyway, spin echo or dynamic decoupling, then you have microseconds. 4 or 5 microseconds, the time scale you have all of a sudden significantly larger, so it's comfortable to do these kind of protocols. And then, if you take these systems to again show you how clean these systems are, kind of similar to the Condella results, we can actually push, if you do coherently, if you do coherent photon generation, then you can push the rate to about, we have achieved something on the order of 200 megahertz rate. And we can't do more than that. You get limited by electronics, but you're not limited by the material. It's the electronics that limits you, but that's the rate at which you can generate photons. If you can collect them all, great. We weren't at the time. And while you're doing this, you have nice and clean G2. And this is the second, Hongo-Mendel interference picture that you're seeing over here, and that gives you about 97. So in terms of benchmarks, you're dealing with a solid-state source, 300 megahertz rep rate, and 97% detector, 97% indistinguishability is your benchmark. Need that. Alex, where are you? All right. Right, so that's not what we're doing today. So I'm not going to talk about this bit, because this is actually using the neutral X tone line. So it's just 2 levels. I should be fair to Alex. It's a 2-level system, so I'm not going to compare that. But it does not spin part of the story. But when you bring the spin part, it gets very complicated, so we don't have those quality results anymore. But nevertheless, we do have something to work with, and that is a three-level system. So what we do is we need to remember, we need to generate a photon, and conditional on that photon, the internal structure has to change. Therefore, we drive the quantum dot transition and emit a photon such that the spin flip has also happened. The ground state changes its projection state. So now I have the condition that if no photon is emitted, the spin is up. If photon is emitted, spin is down. That kind of correlation is there. All right. Now, if I take these photons and just see the quality, that's the G2, pulsed, with a waiting time, and this is the residual. You notice that there isn't a signal there. That's because there is no detector problem that you can account for over here. There's no overlap of peaks, because we've split them well enough. And the main thing is it's a self-limiting, unlike a 2-level system, it's a self-limiting process. You generate a photon and it sits. It's a push button, not a continuous generation, one after the other. So you bring it back in here and then drive. You bring it back here and then drive. So if you don't bring it back, it doesn't come out. So it really is a push button type of scheme, and you have the control over when the photons can be generated. And then we say in this lambda scheme, how good is now indistinguishability of the photons? Here we went a step further. We take 2 separate quantum dots and combine them. We had to match their wavelengths. We do this by electrical contacts. And so in fact, it is fairly straightforward to match quantum dots, one quantum dot to the next. But also the ground state splittings are matched by a magnetic field. And then when you combine the 2 2 photons from 2 quantum dots, the indistinguishability, that's a G2, the indistinguishability is about 93% raw. Now if we do a bit of filtering, which we know where the problem comes in, if we do a bit of tailoring, we get to about 97%. Without having to do anything with cavities. Cavities make this better. But even in the absence of cavities, the sources themselves are that good. So I have 2 independent sources, independent chips in 2 different cryostats, electrically tuned to be identical to each other down to 97% indistinguishability. We use this, before using the 2 separate quantum dots, as a direct, the first example of linking 2 things without proximity. You take a quantum dot and an optical transition of a quantum dot that is spin dependent, and we drove it over a 50-meter fiber to excite a single trapped ion in the next lab. And by 1 photon at a time, the coupling was so strong in this cavity as well that you can see the trapped ion. Maybe it's right here. It's a ytterbium ion. We were able to saturate the ion with a single photon stream coming in from the quantum dot. And then we went a step further, and we brought in the conditionality of the ground state of the quantum dot to what happens to the ion. As in a basis state transfer, the spin up and spin down conditionality over a mixed state approach here. We didn't do it coherently, but it was a simple experiment, because the straight line says the ion and the quantum dot are correlated, and you can see the quality of the data. As far as I'm concerned, this remains the only experiment of hybrid but single quantum species coupled to each other, but in a direct way. Now, the next thing is this the Puppetmaster approach, and that is we have to be over here as the Puppetmaster, and then the 2 identical systems, in this case quantum dots, the photons from the quantum dots are getting indistinguishable in this beam splitter approach. And of course, I should emphasize this, even though it's easy to draw, this is spread over 3 optical tables and 2 cryostats. It's a full lab. All right. So the way it works is that indeed we drive this transition, and then we look at the Raman photon that comes out that does the spin flip between these 2 states that are split significantly, 25 gigahertz typically, and then we look at those Raman photons. And the process is you prepare the spin state, you do a Raman photon generation. Probabilistically, it may or may not generate. That's where the quantum feature will come in. You do a spin rotation here to select the basis you want to make a measurement, so that you can choose to rotate your lab with respect to your spin, and then you make a readout measurement. This highlights how well, it's a 2-photon coincidence. It highlights how well we can tell whether a photon was emitted or not, and how it's correlated to where we find the spin. So if a photon is detected, the spin is flipped, is basically what you're seeing here with 97% fidelity. So that's our fidelity for telling that the spin is flipped, and actually measuring that spin, conditional on the first photon. And then you just have to extend it to a 3-photon case to do the test for the entanglement or the quantum correlations you can generate. And when you do this, in this geometry, you take 2 photons. Essentially, you prepare both quantum dots the same way. You try to scatter a single photon from each one, probabilistically. You choose your basis for each one separately, and then you do their readout. And then when you do this, it's a 3-photon coincidences. In the Z basis, the simplest basis, we get something like 86% visibility when all vectors go in. Now, it is probabilistic in the sense that most of the time, neither emit a photon. We're not deterministically driving them, we're weakly driving the quantum dots. Sometimes only one of them emits a photon, and that's the point, right? One emits a photon, flipping the spin. The other one doesn't emit a photon. You detect one photon, which spin flipped. If you can't tell the photons apart, you can't tell the spins apart, and therefore in this correlated state. But sometimes, of course, by that much error, by the probability that you're driving the system, you get 2 photons emitted, one from each quantum dot. That's bad. That's a fundamental error in your system in this particular approach, and we should see that. And indeed, we do. The up for a finite weak drive, the up probability is always higher than down. That's a fundamental thing that we expect to see, and it's indeed that. But the second most important thing is the up-down and down-up probabilities are the same. This is the first experiment where we actually had to dim down one of the quantum dots because it was just too bright. Because you need to match the brightness of the 2 quantum dots to be exactly the same. Otherwise, you have a priori information or bias that if you detect a photon, it probably came from A rather than B. That breaks down your entanglement. So we had to actually dim one to match the other ones. The first time I told people in my lab to reduce the signal quality. This is the most vulnerable basis, the X basis. This is where your coherence will really die off quickly, but nevertheless we're sustaining about 40%, and we have improved it a little bit now. So the overall entanglement fidelity is about 63% for this experiment. All right. Now the other nice thing about this, of course, is that the whole thing is interferometric. Your laser pulses are split. This are quantum mirrors, if you will. They are single photon mirrors, but the whole process is still coherent. It's a coherent Raman process. So any path difference is mapped into these photon probabilities. So the whole thing is, in fact, a nonlinear quantum interferometer, and that phase is controlled by the path length difference, among many other things. So you control everything else, and then you're only left with a stabilized phase variation of this interferometer. This is when it's not stabilized. This is when we do stabilize it. But once you stabilize that phase to get the high entanglement that you can observe, then you can tune that phase to generate the state that you want. You can almost tailor the state that you want left behind. It doesn't have to be up, down, plus, down. In fact, that's an example of that. As we tune one mirror in the whole interferometer, you can go from psi plus to psi minus, and with local operation, you go 5 plus to 5 minus. You can generate all 4 Bell states for the 2 spins left behind. Now, these are the 10 papers that I'm aware of that have done this before. So why the hell would you do it as number 11? How do you motivate your students to go and do that again? The main point is, of course, not to do it for the first time as a proof of principle, but to actually have results or test or benchmark your system to other systems to see if quantum dots have a chance or not, or gaining improvement or not. This is a chart of Bell state fidelity we put together, reported. If they corrected these papers, they corrected them. If they presented raw, we kept the raw one. Whatever they presented as Bell state fidelity versus entanglement generation rate. How fast can you do this? Remember the millihertz rate. This is down here. This is millihertz right here. Very high fidelity, but so it's great for foundational principles, but otherwise it's limited in terms of time scales. And over here, this is basically where the electron spins in south-assembly quantum dots lie. So it was worth doing in that sense. The fidelity is not as high, it's not very high, but it's part of the scheme that we use. The single photon schemes tend to be lower fidelity with a gain of higher rate. 2 photon schemes is what you want to go for if you have enough collection efficiency or a better readout, more deterministic readout. But the point is, this is equals trapped ions, neutral atoms, NV centers, transmons, and the whole thing is spread over, I don't know, eight decades of rate. So it shows you how different every physical system is. So it's quite likely, I would say it's quite impressive that such large variation is achieved by very different physical systems trying to do exactly the same experiment. You can realize the same experiment with such large variation. But anyways, the point is we do have the highest rate, so that's an advantage. And maybe we should focus on that for quantum dots. Rather than long distance communication, it is high rate generation of small spin clusters through really short distance interactions. This is another maybe more gloomy picture of the same thing almost, Bell state fidelity for the same papers, but for entanglement generation probability. When I push a button, what is the probability that entanglement will be generated? When I convert it into, I factor out the rate at which you can operate physically, then we're still not bad, but we're not the record. The record is transmon qubit in this sense. But more importantly, nothing really beats 1%. We're below 1%. So you have to try 100 times to get one positive outcomes. That says there's a long way to go. How to improve? 30 seconds, I'll very quickly talk about how quantum dots can be improved. That's not a fundamental limit. So we need to increase photon extraction probability. Please look at Condella results. So that if we did put in actually a cavity on top of these things, we would get a boost automatically. But the second thing is prolonging qubit coherence. I won't bore you with that one, but expecting about 10 to 30-fold improvement on photon collection is achievable based on current results. And I'll pass this quickly. You can use the problem in spin coherence, the nuclear spin dephasing and nuclear spin fluctuations. You can use that, turn it around, to use that reservoir, nuclear spin reservoir, for your benefit. If you've heard of these spin-squeezed atoms, Gene Polzik's results, for example, historically, we are now achieving those in a similar sense inside a quantum dot, where the nuclear spin ensemble is squeezed or reduced in variance, well beyond the thermal distribution you expect. And it has a very long lifetime, many milliseconds lifetime. So now you can start talking about two-mode structures. I won't delve into it, but its main importance is if you reduce the variance, spin coherence goes up. We're at 40 nanoseconds now. Again, key thing is in the process of a single photon generation, which is 1 nanosecond, you shouldn't have much dephasing for the spin. And indeed, 1 nanosecond versus 40 is sufficiently large now. So combining those two, as the lifetime for the interesting nuclear spin ensemble, combine those two, protecting your qubit will push our fidelity, it jump that way, and then cavity enhancement pushes it into megahertz. That's what we expect in the next few years to come. So this might be the first system that actually operates measurement-based configuration to generate entanglement at megahertz rate. And there are plenty of other things to do with these systems. They're exciting. Please join a group to do research in this outstanding field. And this is my team. Thank you very much.
Questions for Mete, please. I can see John over there.
How do you get to the X basis? Are you rotating the spin, or are you using some side poles, short exact poles on the?
We come from the top, but it's an X operation. We're far detuned laser pulses, so you can actually rotate the spin. It's almost like an optical Zeeman effect, if you want.
No. So you're rotating the spin and the
That's right.
You get it. Yeah, you're changing the phase.
Exactly.
So at the moment, so the indium gallium arsenide quantum dot is good source and also there's inverter interface, but there's still a problem is it has to work at low temperature.
Mm-hmm.
So can you make comments about in the future if we really want this kind of source or devices can be work at room temperature, for example, use the wide gap semiconductors or two-dimensional material.
Sure. If you've noticed, almost everything I showed had nothing to do with dots. You could have replaced dot with any other source that does what I need, and you could do exactly the same experiment. That's the whole principle of those 10 papers, or 11 papers. The point is your source has to get to that stage. So if you're worried about cold, which is, it's this big, right? And I think it's fine, it's not a problem. But if you are worried about that, then you can actually look into other materials. Now, rather than simple spectroscopy or open-ended spectroscopy, you can actually try to understand and tailor materials that will give you this result. So if your nuclear spins is your problem, go with spinless systems. If your operational temperature range is your problem, go with wide bandgap materials. That's why we're working not on self-assembled quantum dots only, we're looking at 2D materials. The ones we're working on are cold, but they can be, you can increase the temperature quite significantly compared to these ones, and they survive still. And there's some other layer materials, gallium selenide, for example, where it is room temperature operation. The problem is none of them yet operate at the quality that self-assembled quantum dots have, both in terms of spin, if you find them, and in terms of the optics. So there's work to be done there on basic sciences and materials research, whereas the implementation, I think the self-assembled quantum dots are ready for that.
Thanks. I'm afraid we're going to have to move on. So let's thank Mete again.